Hey y'all, welcome to part two of the notes. Congratulations on making it this far. Now we're talking about accuracy and precision, which are two words that mean something really specific when a scientist says them, which makes it kind of tricky because they're similar to each other, but they each have a really specific meaning. But before we get into that, there's a really important point you have to understand, and that's that no measurement is perfect. Every measurement has a little bit of error in it, and every measurement really is an approximation. Some approximations are better than others, and the terms precision and accuracy are going to help figure out how good an approximation is or how good a measurement is. You may have heard of this term called significant figures. I'm not going to fully explain that. If you take another science class, particularly chemistry, you'll learn a whole lot more about significant figures. But that just means that scientists treat numbers a little bit differently than math people do. So to a scientist, the number 6 is different than the number 6.0, which is different than the number 6.000. And a mathematician would say those numbers are all equal, but a scientist would read those differently. They have different numbers of significant figures or different numbers of precision, different amounts of precision. That's a confusing idea, but I promise I'm going to explain it in detail and I'll tell you what you need to know. So first, what's the difference between accuracy and precision? So accuracy is how close a measurement is to the actual value or to the true value that you're trying to measure. And precision is different, and that's how close repeated measurements are to each other. So if you take a measurement 5 times and you get numbers that are really close to each other, that would be high precision. It's possible to have precision without accuracy, just like the dartboards down there. If you are trying to hit the bullseye, an accurate throw means that you're getting close to the bullseye. Precise or precision means you are getting close to the same spot every time. So the dartboard on the left has high precision because those darts are clustered really closely together, but it has low accuracy because it's not close to the bullseye. The one in the middle has high accuracy but low precision because they're not clustered, so it's not very precise. You're not hitting the same spot every time. You don't have it dialed in, but it actually is accurate, even though most of them aren't in the bullseye, because if you look at the average position, on average, they're very close to the center. So it's possible to have one but not the other. The goal, obviously, is to try to get high accuracy and high precision. So on average, they're in the bullseye, but they're also clustered really tightly together. That's a good way of thinking about accuracy and precision when you're making measurements. So let's talk a little bit more about uncertainty. So that's what I was hinting at earlier. Basically, no measurement is perfect. Every measurement has some uncertainty, or every measurement is an approximation. Here's where some of that significant figure stuff creeps in. So in scientific measurements, uncertainty is represented by the last digit in a measurement. So here's an example. If you put something on an electronic balance, that's what we call it, an electronic scale. Scientists call it a balance. And that balance reads 24.53 grams. That is an approximation. It doesn't mean that the object is exactly 24.53. It means that it's pretty close to that. So follow-up question. Of course, you want to know, all right, how close is it? How good of an approximation? Well, in science, we can assume that the uncertainty is represented by the last digit. So that means that even the balance is estimating or guessing that what the last digit is. So if we see 24.53, that means that the real object is somewhere in the range of 24.5 to 24.6. But where within that range, that's where the uncertainty of the device or the estimation comes in. So it's somewhere in that range because we know the first 3 digits are true. So greater than 24.5, less than 24.6. But we don't know exactly where. We know it's close to 24.53. So what does that mean? Well, that means one, when you're looking at a scientific measurement, you should know that the uncertainty is in the last digit. But that also means when you are making a measurement, you have to include the right number of digits. And that's going to reflect how precise whatever instrument you're using is. So that's a complicated idea, but I'm going to make it a whole lot simpler. I'm going to explain in detail. Here are a couple examples. So these are two balances that are both reading the mass of this little metal cylinder. You can see on the left, we've got 34.70 grams. The uncertainty is in that last digit. So we know it's close to 34.7. The balance is estimating 34.70, but we know that it's close to that. The balance on the right says 34.7191 grams. That is a much more precise measurement. And we say it's more precise because it shows you more digits or more decimal places. And the uncertainty is assumed to be in this last digit here. So it knows that it's really close to 34.719 something grams. It doesn't know exactly, but it's close, and it gives you all this other information. So this one on the right is considered to be more precise because it takes the range of uncertainty and narrows it down to the tenths, hundredths, thousandths, 10,000ths place of a gram, which is really small. That's very precise. This one over here is only narrowing down the uncertainty to the hundredths place. So this one would be less precise. This one would be more precise. Which one is more accurate? Well, we don't exactly know given the information we have, because unless we know the true mass of that cylinder, which maybe we're never going to know that, we don't know which one is technically more accurate, but we can tell you which one is more precise. Here's another example. Say someone asks, how far away is your house? And you get a couple different answers. Oh, my house is 2 miles away. If someone tells you that and you're trying to go to their house and you're looking at your GPS or the odometer on your car or whatever, and you go about 2 miles, maybe it's a little more, maybe it's a little less, but you think you see their house, you're probably right. They just said 2 miles. If someone says, oh, my house is 2.5 miles away, that's a more precise answer. So that tells you that it's very close to halfway between 2 and 3 miles away. And if someone tells you my house is 2.53761 miles away, that's an even more precise answer. And if they give you all that extra information, all those decimal places, you're going to be looking in a really specific spot. So that's another example of precision and how a more precise measurement can show you where the uncertainty is. So what does this mean for you when you're actually making measurements in a lab? To figure out how many decimals to include or how much precision you should include in a measurement, you just need to know how to correctly read a measuring device. Yes, we are going to talk about how to read a ruler, how to read a thermometer. You probably have done that before, but maybe you've not done it the technically correct scientific way. So let's have a look. These are a couple different examples of rulers, and this is similar to the example of electronic balances, but it's true for devices that are not electronic as well. So you can see the top ruler here has centimeters. They both have centimeters on them. This one lists the tenths of centimeters in between, and this one down here only lists the half of each centimeter in between. So because the smallest unit here is tenths, this one is more precise because the smallest unit or the smallest increments marked on it are smaller. So smaller increments means more precision. All right, everyone, I have an important announcement to make. This next slide is really important. This is what it's all about. This is how you actually read it. So make sure you're paying attention to this. Always estimate one digit beyond the smallest increment marked on the device. I'll show you exactly what I mean. Here's our first example. This is a thermometer reading a temperature in degrees Celsius. So that's actually pretty hot, almost boiling. And the rule is to estimate one digit beyond the smallest digit that's marked. So let's figure out what the smallest increment is. We have 80 over here. We have 90 over here. And if you look, we've got 81, 82, 83, 84, 85, 86, 87, 88, 89, 90. So each of these lines is 1 degree Celsius. So if the smallest unit on the device is 1 degree Celsius, we need to estimate one place further than that. Smaller than the units would be the tenths. So when we record a temperature with this thermometer, we have to include exactly 1 decimal place. Well, what's the answer? You got to estimate. That's the whole point. We don't know exactly where this line is between, let's see, 85, 86, between 87 and 88. So we have to estimate. Maybe that looks like 87.6 degrees Celsius. So a couple things here. One, notice that I included exactly 1 decimal place in my estimation. Notice I also included units because every measurement needs a number and units. And the way we knew to include 1 decimal place is by looking at the smallest increment that's marked and going 1 decimal place further. So here's some uncertainty. We know there's uncertainty in this last decimal place because if someone else read this thermometer, maybe it looked like 87.5 to them, or maybe it looked like 87.7. The point is there's some estimation involved, which is why this measurement says we know it's between 87 and 88. We estimated it to be 87.6. Here's another example. This is a graduated cylinder, which is used for measuring volumes. So all the same rules apply, except when you look closely at a graduated cylinder, you'll see that the water level or the fluid level for whatever you're looking at is not completely flat. It has this curved shape called a meniscus. So how to read that is by looking at the bottom of that U-shaped meniscus, not at the top. So if you look right at the bottom, try to figure out what line it lines up with, and then make your measurement accordingly. They're calibrated so that the lines will line up with the bottom of the meniscus. But we've got another problem. Let's say this lines up exactly with this line right here, which would be 10, 11, 12, 13 milliliters. Let's say it's exactly even with that line. Well, what do we put? 13, 13.0, 13.0000? Don't just guess. Here's how you find out. Again, look at the smallest increment. Each line on here is 1 milliliter. So go 1 decimal place further than that, which would be tenths again. So if you think it lines up exactly on the 13 line, you have to mark it as 13.0 milliliters. Same reason as before. Smallest increment is the whole unit or the whole number, units. So we go to the first decimal place. Here's one more. This is a centimeter ruler. And this is also typical of the rulers that you're going to see in class. So we have centimeters marked. And the next, the smallest increment is tenths of centimeters, which means we're going to have to go 1 decimal place further, which would be the hundredths. So here we can see we've got 4.1, 4.2, 4.3. This candy cane is somewhere between 4.2 and 4.3. If we use this line here, we have to estimate where between those using exactly 2 decimal places. Maybe you say 4.27. Someone else could have looked at that and thought maybe it's 4.26 or 4.28. And that's okay because there's uncertainty in estimation in the last decimal place. But anyone that reads this ruler should have exactly 2 decimal places, no more, no less, because the smallest increment is the tenth of centimeter. So that is probably a new skill for most of you. And to practice it, we're going to do lots of practice questions. But if you come back to these examples, they should help you figure things out. And if you have any questions, don't hesitate to let me know.